There we go. For chapter 3, deals with exponential functions and logarithms. Okay? So, just by looking at a function, not its graph, but at a function, how can I tell it's exponential?
It has an exponent.
Well, x squared has an exponent. Is that exponential?
Yep. Why not?
The exponent is a variable. X squared is a quadratic. X cubed is a cubic. Exponential means it's growing much quicker than that. Your actual variable is in the exponent. So if it looks something like this, where I have a to the x, a being a number greater than 0, why couldn't a be 1?
Because it'll always be 1.
Because it would always be 1. 1 to anything would be 1. You just get a straight line. Okay. So just to make sure everybody's on the same page, get your calculators out. Make sure we're typing this in right so that it shows up. So if I want to look at evaluate each function, now I want you to be consistent for this. So the test, everybody has the same answers, and your answers match the book. The book will always go to 3 decimals on this stuff, just to be consistent. So go ahead and find those 3 values for me, rounded to the 3 decimal places. Anybody else get that for the first one?
Yes.
Okay.
Yeah.
0.354. Everybody have those 3? Anybody have a problem getting those answers?
Yes.
Which one did you type in wrong?
I had error. But number 3.
For the third one? Did you do 0.8? Did you do a negative sign or a minus sign by accident? Yeah, I think that's a minus sign. Try 0.8 and make sure you get negative instead. But yeah, it looks like you had a minus sign. Okay. So, now, graphically, if I look at these 2 functions and how they compare to each other. Now, if I graph these, I'm going to get one function like this, and one function like this. Which one of those is which?
5 is the one that grows faster.
Yeah. 5 to the x is accelerating vertical faster, so that's going to be 5 to the x. This is going to be 3 to the x. What point do they share in common?
0.
Say again?
X is equal to 0.
Well, what coordinate is that? 0, 1. Yeah. These will share a 0, 1 in common, because anything to the 0 power will be 1. Okay? If you do these 2 instead, 3 to the negative x and 5 to the negative x. What's that going to change? What do you mean the direction?
Going down?
Yeah, instead of exponential growth, it'd be exponential what? Decay. The idea is they still have the same steepness, just going downhill now instead. So roughly like that, and like that. And if they're both hitting a 1. Okay. Now, the book will actually keep doing this. They'll do a negative exponent. Rather than doing a fraction as the base, they'll quite often do these as, they'll limit a to being a number bigger than 1. So you don't deal with fractions between 0 and 1 for the most part. But then they'll say that it's a to the x. Now this has all the, a lot of these will have the same properties. Domain's all reals, range is all non-negative reals, y-intercept is 0, 1, and it's increasing over the life of it. Okay? Has a horizontal asymptote at the x-axis, and it's continuous. Exponential decay, the only thing they'll change is their default formula has a negative exponent. Rather than dealing with a fraction from 0 to 1 being the base, they just make it a negative exponent and limit the base to being greater than 1. Okay? Then they base everything around that. Domain's the same, range is the same, y-intercept is the same. The only difference is it's decreasing over the length of the line. Okay? Now, the nice thing about these, all these exponentials will pass the horizontal line test. Because of that, we can define them as one-to-one. Which, what that means is one property allows you to actually rewrite any of them. If you have two that are equal to each other, you can rewrite them until they have the same base. If they have the same base, then their exponents must be equal, assuming the two lines are equal. So this one-to-one property, what this means is you're going to solve problems like this. And this is the first thing that I would expect to directly see on a test in this format. If you have 16 equals 2 to the x plus 2, the idea is I can cheat a little bit. Using the one-to-one property, I can rewrite 16 is 2 to what power? 2 to the 4th. So I really have here 2 to the 4th is equal to 2 to the x plus 2. So what does that mean? Yeah, 4 is equal to x plus 2. The two exponents are equal to each other, which, yes, does mean the solution is x equals 2. Okay? Now, I'm just bypassing the irrelevant information. For this one, I have 1/3 of the x equals 81. What's the common base? 3. Because 81 is 3 to what power? 3 to the 4th. 3 to the 3rd is 27. 3 to the 4th, 81. This is that section, this chapter where it's going to be really convenient to know some basic powers up to about 5th, 6th, depending on the base. Okay? It makes it easier. 1/3 is 3 to what power? -1. So this is 3 to the -1 raised to the x. Now what do you do with power when you're raising it to another power? Multiply. So this is really just 3 to the what? -x. And 3 to the 4th, that means -x is equal to 4, and x is equal to -4.
What good does it do us that x equals 10?
What that means is 1/3 raised to the -4th will give you 81.
Why don't I just plug that in my calculator?
What are you plugging into your calculator?
I don't see how this is useful. Just keep going.
Because when we get into logarithms and stuff, you're going to need this. But this is a way to solve simple problems.
Okay.
If you can manipulate them to get the same base, you can do this process. It's a one-to-one property. Now, graphically, transformations, all your standard transformation rules apply. So if I have a parent function that's 4 to the x, 4 to the x minus 2 is going to do what to it? Shift it 2 to the right. What about if I have -1/2 out front of the 4 to the x? What is that going to do to the graph? It'll flatten it. It'll compress it vertically by what factor? 0.5, yeah? So vertical shrink or compression, if you like, by a factor of 1/2. And what about the negative, though? Flip it how? It's out front, so it's affecting it vertically or horizontally? Vertically. If it's on the x, that's when it affects it horizontally. When it's on the entirety, that's going to affect it vertically. So it's going to reflect vertically, which is over what axis? The x-axis. So it's also going to reflect over the x-axis. What about this one? It's going to do what now? So the negative sign is going to reflect it over what?
Y-axis.
The y-axis, which will change it from growth to decay. So I think that's what you're getting at. So it's going to reflect over the y-axis. Down 3? Up 3. Remember, the vertical is going to do whatever the number flat out says. The horizontal is when it does the opposite behavior than what the number implies. That's why -2 inside is going to go right 2, plus 3 outside is going to go up 3. Okay? Questions on those? Okay. Now, you do have a base that shows up quite often, which is E. Remember what E stands for?
No. Just a number.
Well, it's a guy's name, actually.
It's got a name.
Yep.
We named the number.
No, the number's named for the guy. It's Euler's number. Okay? That's why it's an E. Euler.
Stop.
So, this is what's called the natural base. This one shows up a lot whenever you have to have any kind of continuous growth. Instead of like doubling every month or things like that, this is when you have continuously growing values. Okay? Now, where on your calculator do you have that E button?
Somewhere. Oh, I see it. It's the division one.
The division one gives you e to the first power, but you also have e to the x somewhere on there.
Oh.
Under natural log. It's the inverse of natural, or the second in natural log.
Trying to find it.
Left side.
Oh, there it is.
So, go ahead and find, skip those two. Go ahead and find e to the 6.2 and e to the negative 0.4. Just the top two. What's e to the 6.2?
493.749.
Everybody else get that? What about for the next one?
0.961.
Everybody else? Okay. Those two values. Now, where these are often used, actually we'll get there in a second. If I look at the graph of this, just a rough sketch of this graph. Is it exponential growth or decay?
Grow.
Growth, because e is a number bigger than 1, and you have a positive exponent. So if I graph this, what's its y-intercept?
1. Not 1.
Not 1.
0.
Y-intercept will occur when you make x 0, or in this case t 0. So 0 times 0.17 is 0. E to the 0 is?
This is 0, right?
E to the 0 is? 1. Anything to the 0 is 1. 5 times 1 is? 5. So this graph
5.
intersects there at 5. So it ends up looking like, roughly, since it's a growth problem, that. Okay, rough sketch for exponential growth and decay. There's really not too much you can do with it besides plot where the y-intercept is and then illustrate whether it's growth or decay going on. Okay, if they're asking for a rough sketch. Main place this gets applied, especially the E value. Compounding continuously can affect you severely in real life.
Positive or negative?
Usually negative. The problem is when you start talking about investments and the rates of return. Anything you invest is pretty much calculated on, so if you put any money into CDs, into savings accounts, those kind of things, those are going to be compounded on a set number of times per year, quarterly, monthly, things like that. Where do they compound continuously at? Credit cards, debt. Which one of these probably ends up generating a more interest?
Continuous.
The continuous one. Yep. So, if I look at this situation, where on a day of child's birth, a deposit of 25 grand is made in a trust fund that pays out at 8.25% interest. Determine the balance in that account on the child's 26th birthday if it's compounded these three ways. These two formulas I would expect you to know already. The PERT formula for compounding continuously and your general interest formula. If you don't have them memorized, get them memorized.
What do they do?
Compounding interest at some set number of times per year and compounding interest continuously. So for this, quarterly would be how many times a year?
4.
4. So if I'm going to write this equation, I want to figure out how much you end up with. What's the P stand for? Principal. In this case, what's that number?
25 grand.
$25,000. So, times 1 plus, what would the R be?
8.5. Or 0.25.
8.25? No.
Why not?
What would it be? 0.0825. Make sure you change it to decimal form.
Oh, wow. That never mind.
N for quarterly. 4 times a year. Raised to the same N times, what's the T? Time, in this case, 26 years. Is it tight? So, plug all that in. What do you get? So how much does the kid get on his 26th birthday? It's a decent number.
$208,941.65.
Anybody else get that? Yep. $208,941.65. Now, admittedly, 8.25% is a pretty good rate of return. Stock market averages about 7% over its lifetime. So, 208,000, that's a pretty good rate of return over that amount of time. That's why you start saving right when you get a job. Because those 26 years or a lot longer before you retire builds up a lot. Monthly, what would I change?
4 to a 12.
Change the 4 to a 12. Change the 4 to a 12. Go ahead and do that. Figure out what you get.
$211,989.34.
How much? For the cents?
34.
34. Anybody else get that?
Do you want this in triple decimal too?
Considering it's dollar and cents, no.
Good answer.
Continuously. Now, admittedly, if we still had mills, then I'd probably have you do down to the thousands. But we no longer have tenth of a cent pieces.
Are you serious? That was a thing at one point?
Yep. Called a mill. Continuous, you'd use the other formula for. What does continuous come out to be? Anybody? Nobody wants to venture a guess? Shouldn't be a whole lot bigger than the last one. But it should be bigger.
213,551.
That's not what I got. Let me see your calculator.
Anybody else get that? Yeah.
Oh, you can do it all at once.
That's what it should be. Okay. One more. Decay. Honestly, this is where you see it most often, this type of problem. Half-life of the Q formula represents the mass of radium 226. Half-life of 1620 years. The quantity of radium present after T years is given by that formula. I'm honestly not going to worry about the graph too much. You can punch this in and adjust your window accordingly. But if I want to determine the initial quantity, what's the initial quantity going to be here?
I have no idea.
Stop and think for a second. It's actually the same as the interest problem you just did, but your rate of return is 0.5. So the 1 minus 0.5 is 0.5. So the initial amount, also known as what if we were talking money?
16.
What's the word I use though? Principal. It's the same idea. Whatever your coefficient is out here on the base, that's going to be your initial amount. So it's just 16. They don't give units. I would assume grams. And if we're talking kilograms, that's a heck of a lot of radium. But determine the quantity present after 1,000 years. What would I do for that? Yeah, plug in 1,000. Go ahead and plug in 1,000 to the formula. It should be more or less than a half. Or more than less than 8 grams, I should say. Which one? More or less? The half-life is 1,600 years, and we've only going 1,000 years. Should it be reduced to half its original amount yet? No. Talking about generalities, to be able to look at it and know if you screwed up or not.
Half-life?
For half-life, because it takes 1,600 years to get down to half of its original amount. That means if I put in 1620, this is going to give you 8 grams, right?
It's going to be more than
So it should be more than that since we're only going 1,000 years. What is that amount actually going to be? Anybody?
10.43.
10.43 grams. Questions on any of this stuff dealing with exponentials? Okay. The rest of the time is yours.